All right, we're going to solve these problems that are weak acid, strong base. And in our Erlenmeyer flask is a weak acid, and in our burette is a strong acid. So when it says 0 milliliters of the base has been added, it's really saying that nothing has come from the burette, so we're all the weak acid. And we know how to solve weak acid pH calculations. So it's nothing but the acetic acid, and it's going into these ions. We have 0.25 molar of that. Doesn't matter how many I have or how much I have of it. 100 milliliters or 10 milliliters is going to have the same pH. This is going to be x squared over 0.25 molar is equal to 1.8 times 10 to the negative 5. X is 2.12 times 10 to the negative 3. That is going to give me my hydrogen ion concentration. I can get my pH of 2.67. So that makes sense. My initial concentration would be acidic. All right, so let's go and let's add some base to this. This is how much base we added to that. It's really important that you get it into millimoles because that is actually a good comparison. Notice that I added more of the base, etc., than I have of the acid. But when you look at the millimoles, I have more acid than I do of base. So this is why we're comparing millimoles. So I've added the base, so I've added the hydroxide, and what's going to neutralize is this weak acid. It's going to make water plus the acetate ion. So I have 6.25 millimoles of the base and 12.5 millimoles of this acid, and nothing on the product side. I want to completely neutralize this, so it's going to use up, all 6.25 of that from the base, going to get it down to 0 because I have that amount of acid to react to it, and it leaves me with 6.25 millimoles of the acid. But when these react, it's making some product, so here's the 6.25 on this side. My habit is, once I get the new millimoles, I immediately put it back into molarity. So I get a 0.056 molar here. I divide it by 112.5 on this side, and I get 0.056 molar on this side. So get the new millimoles divided by milliliters. Boom! You're in molarity. I want to use the Henderson-Hasselbalch equation, and it did require things to be in molarity. That's why I had to put that in there. So my concentration of my acid and my base is in molarity. Take the negative log of this Ka. The Ka was given to you up here in the problem. So that's going to be 4.74 plus log of 0.056 of the base. Here's your base, right? That negative, it's telling you it's the base. And the acid is over here, 0.056 molar. So that's the acid and its conjugate base. This cancels each other out. My pH is 4.74. I just calculated this part right here. The next part in this series is going to be the equivalence point. So when I take a look at my equivalence point and I multiply these together, I should get the same amount of acid in the base. So I have 12.5 millimoles of this. I have 12.5 millimoles of the acid. Remember, these are individual problems, starting over from scratch. This is what I'm looking at. All right, so I know I have the same amount in millimoles of this. That's your equivalence point. Now let's take a look at the equivalence point for these weak acids. Strong base calculations. This is where you're going to write a hydrolysis reaction. So at first I'm dumping the base in there, and it's being neutralized by this acid, and it makes water and the acetate ion. I have 12.5 millimoles each of the base and of the acid, and nothing on this side. I want to completely get rid of the hydroxide, and I'm able to because I have enough of the weak acid. It means, though, I'm going to add some over here on the product side. I now have 12.5 millimoles, and I only have this in my Erlenmeyer flask because all of this has been used up. What do I do next? Boom, get it back into molarity. Divided by the total volume that you have now in your Erlenmeyer flask. It came from two sources, and I get a 0.071 molar. I'm now going to write my hydrolysis reaction because it's the only ion that I have in here. And it looks like this. Ooh, Kb is needed. I wrote a hydroxide. Boom, Kb. Put it in there. 5.6 times 10 to the negative 10. My initial concentration, I have it in molarity now. I don't have any of this. This becomes a regular ice table calculation. All right, and so this now is x squared over 0.071 molar. Lucky I recognized I needed my Kb because a hydroxide was made. So when I do these calculations and I get my x, I have to always take a moment to think, what is my x telling me? It is telling me that it's a hydroxide. I always have to orient myself to that, because if you don't, there's just a tendency to always think it's a pH or a hydrogen ion concentration. This is my pH at equivalence. That's interesting, because we said it would have a basic pH at the equivalence. A basic pH at the equivalence point is a typical WASB. Good test question. All right, so we went through this part. So remember, all of it gets neutralized, leaving you only with the acetate ion. Boom, get it back into molarity. 100% is all I have in here. I need to write my hydrolysis reaction. Boom, I have a hydroxide. I need a Kb. Solve it like an ice table. Just remember, when you get your X, what is it really telling you to be able to get your pH? Think about where you are on this graph, where you are on this titration curve. The last one I'm going to do is this excess amount of base. So when I do this, I have 20 millimoles of this, and I have 12.5 millimoles of this. So clearly I have more base than I have the acid. So I know that I'm going to have a basic pH. So we say that there's an excess of hydroxide, because I have way more than that. So 20 millimoles minus 12.5 millimoles, it's going to neutralize as much as it can, divided by the 250 milliliters, and I get 0.0375 molarity. I can get a POH is 1.42 and go on and get a pH 12.6, which I knew was going to be basic because that's where we are in the over-titration part of this. So this makes sense. Yay, I'm feeling happy. All right, let's do another one. Okay, I like to orientate myself, what is what. And in this particular example, we have hydrofluoric acid in here. And the type of base we have is KOH, so strong base, strong out, or weak acid. All right, we added no base. It is all a weak acid, so it's a weak acid pH calculation. You know, when you dissociate that weak acid, we start with 0.3 molar, nothing of that. Eventually it makes some on the other side, and so it becomes x squared over 0.3 molar is equal to the Ka, 6.6 times 10 to the negative fourth. So when I finish this and I get an x of 0.014 molar, I know that it's equal to the hydrogen ion. It's giving me that concentration. I can easily go on and get a pH from that information of 1.85. I am at the initial part of that. I'm going to go to this halfway point here. Take a look at this. Get it to millimoles. 3.75 millimoles, and I have, again, starting here with 7.5 millimoles. I have added a strong base to my Erlenmeyer flask, which has hydrofluoric acid, and this is the equation that's going to follow, right? He's going to neutralize the base that I added. I only have hydrofluoric acid in there. The millimoles that I have on here is 3.75, on here is 7.5, and I have nothing so far on over here. It's going to completely neutralize this because I have enough acid to do this, that it leaves me with 3.75 millimoles of the acid. But it also means I'm making some on this side. So I have 3.75 of the fluoride ion over here. What do you do when you get to millimoles? Boom, get it back to molarity. So I'm going to add up the total volume in here, and that's 37.5 milliliters, gives me 0.10 molar. I'm going to divide this by 37.5 milliliters, and this gives me 0.10 molar. Cool. Now I'm going to do the pH, which is the pKa plus the log of the base and the acid. So I'm using the pKa, not the pKb, pKa, plus log of the concentration of the base over the concentration of the acid, and they beautifully cancel each other out. And I now have a pH of 3.18. So I started at 1.85, and I'm now up to 3.18. The next one is going to be that equivalence point where they have the same millimoles of each. So let's take a look at that one. All right, so we have this. When I do the millimoles of this, I have 7.5, and it exactly matches the 7.5 millimoles of this. So remember, at this equivalence point, we are going to write the hydrolysis reaction. We know that's going to happen at that point. So I don't know, I just like to keep things consistent, knowing that the base reacted with the acid to make these two products. I know I started with 7.5 millimoles of each on this and 0 of that. Luckily that I have enough acid to completely neutralize that base, but don't forget I'm making some of this product on this side. So now I have nothing but the fluoride ion, so I have millimoles of that. And what do you do next? Boom! Put it back in the molarity. So I'm going to divide it by the total milliliters I have, and this becomes 0.15 molar. Now I write that hydrolysis reaction with that fluoride ion to make HF plus OH. Oh, Kb. Wrote a hydroxide. I need a Kb. That's 1.5 times 10 to the negative 11. Put my initial amounts here because I'm in molarity now, so that's a good thing. And a little bit of that's going to come make off some of this other stuff on the other side. Like I said, I feel like I'm cooking. A little bit of this makes some of that. So it's x squared over 0.15 molar is 1.5 times 10 to the negative 11. Keep track of what your x is going to tell you, because my x of 1.5 times 10 to the negative 6 is a hydroxide ion concentration. So again, I have to find the pOH before I can find the pH. And that's interesting because, again, we're at the equivalence point. We're in a weak acid, strong base titration curve. This has a basic pH equivalence point. Great test question. All right, now we're going to go to this part of the graph where I've over-titrated it with the material that's in the burette, which is the strong base. So when I do this, I have 60 millimoles of this. Again, I still have 7.5 in here because it's just considered a new problem. I have an excess amount of the base. So when I do this, I'm calculating the concentration of the hydroxide now, because that's really all I have. So this 60 millimoles, yes, it was neutralized by the 7.5, but it certainly left a lot of it over of hydroxide. I divide by the total volume I have, and I get 0.05 molar. Again, it's the hydroxide. So my pOH is 1.30, and my pH is 12.7, which makes sense that I would have a basic pH because that's where I'm ending. I put a lot of base in it that's overwhelmed the amount of acid I had to begin with, so this makes sense. So make sure the pHs you're calculating are making sense. I started acidic, getting a little less acidic, becoming more basic. Just make sure. It's sort of like a checkpoint.